This series of demonstrations showcases the real-world impact in the automotive domain of privacy-preserving federated learning enabled through Trustee. Through encrypted federated aggregation, participating automotive stakeholders collaboratively train advanced localization models without sharing raw data. The resulting global models significantly improve vehicle positioning accuracy and situational awareness. In particular, Trustee-enabled federated learning enhances cross-view geolocalization, CVGL, combining ground view and satellite imagery. Cooperative plug-and-play Kalman net, enabling multi-vehicle cooperative localization. These improvements directly translate into safer and more reliable application scenarios. The demonstrations showcase that the global models produced through Trustee's federated learning process approach centralized training performance while preserving data sovereignty and respecting GDPR constraints. The final demonstration of this series presents a teleoperations scenario where enhanced cooperative localization advances positioning accuracy and reduces the risk of accidents, showcasing that privacy-preserving collaboration can be an enabler of safer, scalable, and cooperative intelligence that helps to save lives and prevent damage. This part demonstrates the cooperative plug-and-play Kalman net solution designed for complex autonomous localization tasks. Using the Trustee platform, Kalman net has been collaboratively trained, which is a deep neural network architecture that models the traditional Kalman filtering steps in order to capture diverse system uncertainties across multiple agents. The algorithm consists of two main stages. First, during the local adaptation step, agents refine their individual state estimates. Then, in the combination step, global intelligence is fused across agents. On the left, the bird's eye view shows edges representing dynamically constructed clusters, where the ego agent and its neighbors exchange relative measurements to improve localization in real time. The center panel displays the cumulative distribution function, CDF, of localization errors. The approach studied under Trustee appears on the left. The blue curve represents a cooperative Laplacian method, and the red curve corresponds to GNSS-only localization. Meanwhile, the right panel tracks RMSE trends over time. In the bottom right 3D view, observe the colored trajectories. The red path highlights the high error of GNSS. The yellow path shows our federated learning-based approach, and the turquoise path represents the ground truth. A personalized federated learning scheme has also been explored, in which only the weights associated with the Kalman gain matrix are uploaded and aggregated. This significantly improves communication and computational efficiency, reducing the load by up to 88% without compromising localization accuracy. The resulting PF-Ed Kalman net matches centralized performance, delivering a scalable, privacy-preserving solution for safe, autonomous swarms. This demonstration evaluates the impact of the Trustee framework on cross-view geolocalization performance by comparing trajectories under different training paradigms. The yellow path serves as the objective ground truth baseline. This is contrasted against a full federated learning implementation in blue, where all neural network weights are aggregated, and a communication-efficient variation in green, which utilizes federated updates only for the feature extraction encoders. These are compared against a single client in red that operates exclusively on a local data subset without participating in federated weight sharing. The demonstration interface facilitates this comparison through three synchronized views. The upper panel provides a satellite view orthophoto for global trajectory mapping, while the central panel displays the synchronized ground-level monocular video from the Kitty dataset. A color-coded legend at the bottom right maintains the distinction between our four experimental variables. As the sequence progresses, a significant performance gap emerges. The single client model suffers from rapid stochastic drift and cumulative translation errors. This failure illustrates the data silo problem, where isolated training lacks the distributional diversity required for robust localization. In contrast, both federated learning schemes remain tightly aligned with the ground truth. The high precision of the encoder-only implementation is particularly significant. It proves that sharing latent feature representations within the trustee framework is sufficient to achieve global convergence. These results validate that federated weight aggregation effectively mitigates local overfitting, providing a scalable, privacy-preserving solution for high-precision autonomous navigation.
What we're about to demonstrate is a scenario known as teleoperation, a crucial backup mechanism for autonomous vehicles. Teleoperation comes into play when highly automated vehicles are navigating on their own, but encounter a situation they cannot confidently resolve. In such moments, a remote human operator can step in, assess the surroundings through onboard cameras and sensor feeds, and temporarily take control to guide the vehicle back to safety. But for teleoperation to be reliable, one element is absolutely essential: precise localization. And this is where our solution makes a difference. Using the Trustee platform, we enhance localization through cooperative localization, where vehicles collaboratively train CalManNet via federated learning. This enables the system to learn how uncertainty behaves in real-world environments, dramatically improving positioning accuracy, especially in dynamic, unpredictable scenarios. With better localization, teleoperation becomes faster, safer, and far more effective. Now let's look at the teleoperation interface that supports this process. On the left, the operator sees a top-down map of the entire road network, with every autonomous vehicle displayed in real time. On the right, the system reports the current localization accuracy, in this case, 1 meter, along with details of the selected vehicle, such as its speed, position, and lane. Below that, a live event log records system updates. In the lower corner, the operator's control station is shown, equipped with a steering wheel and a multi-screen setup, enabling seamless and precise remote control whenever intervention is required. We begin with a scenario in which localization quality is poor. Here, the vehicle operates with a 5-meter position uncertainty. At this level of inaccuracy, the vehicle might appear to be anywhere across several lanes at once. It cannot reliably detect lane boundaries or road junctions, leading to confusion and potential safety risks. As the vehicle begins to move, its uncertainty causes it to drift into the oncoming lane. On the left, you can see the real-world behavior. The car, misled by the lack of clear markings and poor localization, unintentionally enters the wrong lane. This example highlights how quickly things can go wrong when localization is unreliable. With a 5-meter uncertainty, the system cannot accurately recognize that the vehicle has crossed into the wrong lane. This lack of awareness can lead to dangerous situations, potential collisions, severe accidents, and even fatalities. Moving to the second scenario, we now examine the same situation, but this time with the vehicle operating under high-precision localization. On this slide, we see scenario 2, where the vehicle navigates with less than 1 meter of positioning uncertainty, enabled by the enhanced localization provided by the Trustee platform. With this much lower uncertainty, the system now knows the vehicle's position with confidence. So the moment the car begins to drift toward an unsafe area, it immediately recognizes the deviation and triggers an alert to the teleoperator. Although the vehicle follows the exact same trajectory and makes the same mistake as before, this time the system can correctly interpret that it has entered the wrong lane. Because the uncertainty is dramatically reduced compared to the 5-meter case, the vehicle's true position is now unmistakably clear. On the screen, an intervention required warning appears, highlighting the affected vehicle and showing that it has been automatically brought to a stop. This level of situational awareness is only possible because the localization safely back onto the correct trajectory. Once the maneuver is complete and the environment is safe again, autonomous mode is restored, allowing the car to resume normal operation.